Lewis' theory focuses on valence electrons and uses the octet rule to predict molecule formation. The problem with the octet rule is that there's so many exceptions: expanded octets, incomplete octets, free radicals. When you have a theory with a lot of exceptions, you begin to question the theory itself. So valence bond theory is a little bit different. In valence bond theory, the shape of the molecule is determined by the extent of the overlapping orbitals. We could also say it's determined by the number of overlapping orbitals. And in order for the bond to form, we need to see a lowering of the energy of the system. And the other thing to know about valence bond theory is that the electron density is localized. The localization of electron density in order to form a bond is pictured here. So first we would start with, say, two s orbitals, and we have our probability density maps pictured here. So with all the little dots representing the probability of finding an electron. And as these two atoms, as these two s orbitals begin to overlap, we see a darkening of the area where the bond would be located. And that darker area represents a higher probability of finding now the two electrons in that area, and that also represents the bond. So we know that the electron density then is localized in that general area where we would expect to see the bond. The idea that we're going to study the hybridization of orbitals may be a little bit intimidating. So this image up here is to remind you that a hybrid orbital, the definition is the same as other hybrid situations. So for instance, we have two breeds of dogs, and we can mate them to create a hybrid breed, which has the characteristics of both of the original breeds. Same thing happens with our orbitals. They're going to look a little bit like the parent orbitals. Why hybridize? Hybridization is used to explain bonding when several different types of orbitals overlap. The caveat is that these orbitals must be half filled. They must contain one electron. And remember, each orbital can contain a maximum of 2 electrons. So the orbitals must be half filled in order to participate in bonding. The hybrid orbitals occur when an atom promotes an electron to a different orbital in order to gain more half-filled orbitals. Let's unpack that last statement a little bit by looking at the electron configuration and electron configuration energy diagram for carbon. So, electron configuration for carbon. We're going to start with helium, 2s2, 2p2. When I fill out the energy diagram for carbon, I'll put 2 electrons opposite spins in that 2s orbital. And then I'm going to put the other 2 electrons in the 2p subshell, and I'll fill individually. So what's the problem with the standard orbitals for carbon? What's the problem with our current electron configuration? Well, we know that in order to covalently bond, orbitals must be half filled. So here we have 2 half-filled orbitals, which will allow for 2 bonds. So currently we have 2 half-filled orbitals which would result in 2 bonds. That's a problem because we know from experience carbon likes to form 4 bonds. It has 4 electrons and needs 4 more. So just placing electrons in these 2 spaces wouldn't be sufficient. It wouldn't get carbon up to its octet. So what happens? Hybridization will occur. Carbon's going to take these 4 electrons that were on the 2s and 2p orbitals and now spread them across an sp cubed hybrid orbital. Why is this even allowed? How come you're allowed to just rearrange the electrons like that? And there's also an energy cost here because in order to do this, one of these electrons has to move up to a higher energy orbital. So it's permissible for 2 reasons. The energy level of the sp cubed hybrid orbitals is lower than the 2p orbitals. So yeah, one of the orbitals and some of the electrons had to move up to a higher energy slightly, right? But then you gained energy by lowering the energy of the 3 2p orbitals. So overall, there's been a gain in energy. The system put out a little bit energy, but definitely gained more energy at the end of the day. The second reason why this is permissible, and we know this from studying the electron configurations, is there's stability associated with having all singly filled orbitals, all with the same spin. That minimizes the electron-electron repulsion. So this is a more stable distribution of electrons in these hybrid orbitals than what we are seeing previously with the standard orbitals. The last thing I want to mention in regards to this image is where the sp cubed part comes from. So there's 1 s orbital in the original electron configuration and 3 p orbitals. So this notation sp cubed is like s to the first power to represent that 1 s orbital, and then there's 3 p orbitals, so it's p to the third power. The 1 is understood, so that's why it just turns into sp cubed. Each one of these individually is an sp cubed orbital. So we can say that we have 4 sp cubed orbitals. So we're not losing any orbitals. Over here we have 4 orbitals, and over here we have 4 sp cubed hybrid orbitals. I do apologize for this dark image here. but it's important. What does the hybrid orbital look like? So we started with one s and three p orbitals. And just like the example of the different breeds of dogs, the hybrid dog is going to look a little bit like both of the parents. So instead of having a dumbbell-shaped orbital, we wind up with one dumbbell-shaped lobe. And then this image, I always imagined it to even be more spherical on the other side. So we retain a little bit of the P and then a little bit of the S. But at the end of the day, it's not an S, it's not a P, it's a little bit of both. This is one sp cubed orbital. And we expect to see 4 of them if we have a carbon center. So in something like CH4, we would expect 4 sp cubed orbitals. With single bonds, it's a little bit less of an issue. And valence bond theory, Vesper theory, accurately predicts the shapes of compounds like methane with all these single bonds. How does that look when we have the hybrid orbitals? Well, the 4 sp cubed orbitals are going to combine and retain the tetrahedral molecular shape. The bond angles pretty much stay the same. There's the little sides of the lobes. These sometimes get omitted from some drawings. So they kind of try to show them there, but don't stress if you see a drawing and they're telling you, oh, this is a drawing of hybrid orbitals, and somebody omitted the little lobe on there. It's just hard to depict. What I want to discuss now is issues when valence bond theory doesn't accurately predict the shape. So in order to do that, I'm going to tell you a story about 2 Mandalorians who fall in love. This Mandalorian couple is so in love, and they're a little bit irritating about it. They're constantly touching one another. One day they decide that they want the soles of their feet to touch. So I've put some tape here and taped the 2 Mandalorians together by the soles of their feet. This represents a single bond between carbon and carbon. We've localized the area of overlap. Now, if we draw a bond like this, just one area of overlap, you would tell me that it's 180 degrees between one carbon and the next. And you'd be absolutely correct. Now, there's examples of double bonds. I'll draw C2H4 here. And this is trigonal planar around each carbon, but right here in the center, and our carbons are our Mandalorians, right here in the center, we're still at 180 degrees. So the single bond was easy to explain. That was the Mandalorians with the soles of their feet connecting. But here's the issue. When we introduce that double bond, that means that our Mandalorian couple has to touch another part of their body together. So the tops of their heads need to touch one another, or their hands. And if we start doing that, right, maybe we want their hands to touch. What's happening to that shape? Are we retaining the 180 degree shape, 180 degree bond angle between the 2 carbons when we introduce that second area of localized bonding? And the answer is no. We're going to have to start playing some game of Twister Imagine that it's a triple bond. What if we had carbon with 3 bonds? It's still 180 degrees. But now we need 3 areas of localized overlap. So their hands would have to be touching and their heads would have to be touching. And there's no way at that point that it's still 180 degrees in here. That's the reason why valence bond theory falls apart. And hybrid orbital theory takes over. Because using hybrid orbital theory, we can explain how there's 2 or 3 areas of overlap and still maintain a linear or 180 degree bond angle.